Hello, in this lecture we are going to look at the classification of processor architectures. This is the agenda. We will look at basics of computing, then we will see the Flynn's taxonomy, then we will understand the basics of process, and finally we will have a summary. Let us look at the basics of computing. These are the different types of computers that we see in our day-to-day lives. Most of you have used a desktop computer which a single person uses. Then you also have embedded systems or embedded computers which a appliance user like a washing machine or a microwave oven user uses. We also have a version of a tablet which again a single person uses, typically for entertainment or reading books, etc. Then the more powerful than desktop computer is a server which allows multiple users over the network to use it, and it is suited for bigger workloads. And the typical use of such a server is sharing of files, hosting websites, or a banking system can use such a server. We have already seen in the previous lecture that a supercomputer again has multiple users. However, the users have to submit the jobs which are typically of scientific applications, and these scientific applications are targeted towards solving grand challenge problems. So, to understand this, let us look at the simplified model of a computer. So, it can be divided into three basic parts, like you have the hardware. On the hardware runs the operating system like Windows or Linux, and then under the operating system you can read So, now let us look at a simplified model of a computer. Inside a box is a hardware. This hardware runs the operating system like Windows or Linux, and under this operating system multiple application programs can be run, which in turn is used by the user who then uses the computer through this application software. Now, let us further look at what is inside the hardware. So, inside the hardware you have a processor which connects to the main memory. The main memory consists of data and code, and apart from this you also have an input device from which you can command the processor, and the processor generates output which the user can see on the output device. So, this is what is there in every computer that we saw in the previous slide. Now, let us look at the basic computing model that runs on this computer. We all know that programmers use high level programming language like C, BASIC, etc., Java. So, it may write a statement like A is equal to A plus B plus 1, which means that the variable A gets a new value which is a sum of old value of A added to B and incremented by 1. This is a typical statement that one would write in a C language or any other higher level language. However, CPUs do not understand such languages, they understand machine language, or a 1:1 correspondence for that machine language is the assembly language. The high level language statement is converted to assembly language statement by system software tools like compilers, and the generated code in the assembly language is nothing but a series of instructions. What are these instructions? These instructions like add a comma b and increment a. So, this consists of two parts, as you can see here. there is an opcode and there is an operand. So, here the add and increment are the opcodes, whereas A and B are the operands. In this case A and B refers to the registers. So, the opcode specifies what operation you want to do, like in this case add or increment the value by 1, or it can also, the operand will specify the location of the data. In this case it is in A or B, which are the registers. So, now these instructions, how are they run on the CPU? So, inside the CPU there is an element called as arithmetic logic unit. So, this arithmetic logic unit is the heart of the processor. It can perform arithmetic as well as logic operations. So, this ALU takes a series of instruction, and corresponding to every instruction there is a data, or as we saw operand in the previous slide. So, every instruction has a corresponding data, and when it operates on that data it generates results. This is the way any computer works. For example, the operation to be performed is addition. The two numbers are 2 and 2, that is the data, and the result that you get is 4. Now, let us see where it comes from. So, this instruction and data that we saw in the previous slide, they are stored in storage. The storage is nothing but memory. So, every memory of a computer will typically have one area for storing the instruction and another area for storing the data. The result also goes back in the storage so that it can be used later. So, this is the basic computing model. Now, with this, let us try and understand how Flynn divided the different types of computer into 4 different varieties. So, this was done way back in 1966 by a computer researcher by name Michael J. Flynn, and he proposed a classification of computer architecture based on streams of data and streams of code that we saw in the previous slide. They reside in the memory. So, he proposed that you can have 2 options for instruction. It could either be a single instruction or it could be a multiple instruction. So, these are the 2 possibilities for the instruction. Similarly, there are 2 possibilities for data, which can be single or which can be multiple. So, in this way you can have 4 options, as we shall see in the next slide. The first possibility is that you have a single instruction operating on single data. So, this fits into the definition of a sequential computer which does not have any parallelism, because the instructions are single, the data is also single. So, this is what we saw in the previous lecture, that you have a CPU that forms the basis for building parallel system. So, this unit is what is used in a cluster. Moving ahead, you have a variety where the instruction is single, but the data is multiple. That means, from the data memory, as you can see here, you have multiple streams D1 and D2. These are the 2 streams, whereas the instruction that is operating in every execution unit is different. Here you have I1, here you have I2. So, this kind of architecture is called as SIMD, that is single instruction multiple data. This was used in vector computers like the Cray platforms that were invented in the early 70s. SIMD instructions today are also available in arithmetic logic units, and these SIMD instructions are useful for applications that handle streaming data. Like you have a series of audio samples which have to be operated upon by the same instruction, like MPEG decoding, and that is where these SIMD instructions are useful, because using single instruction it can operate on multiple sets of data. The graphics processing unit or general purpose graphics processing unit like GPU, they use this concept. Then comes the third variety, that is multiple instructions working on a single data. So, in this diagram, as you can see, the instructions are different, however, the same data is fed to both the execution unit. So, this architecture is not very frequently implemented, because some of the uses that it finds is for fault tolerance, that is you use the same data, but execute use on different execution unit using different algorithms to arrive at the same result. If the result is same, then you know that the algorithm that you have used is correct. Similarly, other examples include multiple frequency filters and messages that needs to be cracked using cryptography techniques. The last variety is multiple instruction, multiple data. Here, as you can see, the two execution unit you have, they have independent data stream and they have independent instruction stream and independent data stream. The last variety is multiple instruction, multiple data. As you can see here, there are two execution units. Each execution unit gets its own stream of instruction which operates on own stream of data, which means that these two units are concurrently executing different instruction on their respective data. Most of the parallel computing architectures of today are of these varieties, and as we shall see later, there are two implementations for this. One is called as a shared memory computer, another is called as a distributed memory computer. So, here we have studied 4 varieties of computing architectures as classified by Flynn. Now, these architectures are going to run different types of processes. So, let us first understand again how this works. So, in the simplest form, you can see that the user is using a computer. This computer internally consists of hardware and software. We saw that the software is actually application software which is running on the OS, but for the sake of simplicity we will consider this as a single software which is running on the hardware. Now, these two are connected by what is called as an interface, and this interface is actually allows a program to run on a processor. So, we have the software is nothing but a program that is running on a hardware which is nothing but a processor. We saw that the program is nothing but a series of instruction, and when they reach the hardware or the processor, they are executed. So, this is done through what is called as instruction set architecture. So, every computer has a CPU and that CPU supports instruction set architecture, and the instructions that are written are a sequence which makes a program, and that program is executed instruction by instruction by the CPU. Now, let us understand the basics of a process. Here in this diagram you can see how the source program is actually run in the memory. The source program is written in a language like C or Java. Then a program like C is compiled, and then there is an object code that is generated. This object code is linked by the linker, and finally you get a binary code like a.out. So, this is stored on the disk which is in the form of a program file. Finally, the loader is going to load it and put it in the main memory for execution. So, let us see the steps. As we have mentioned, the executable file in the form of binary is stored on the disk here. So, this is stored with a file name. This file name is known to the user. A typical file name could be a.out, and the user will type the name of this file at the command prompt, and press return. So, once that is done, the loader comes into picture. The loader will load the program at an appropriate location in the main memory and it will transfer control to this program, thus the program is run. Once the program is running, it gets into execution mode, and now this program, which is in the form of a file on the hard disk, when it gets into memory and start running, we call it as a process. So, to accomplish what the program is supposed to do, let us say suppose it is taking an input file which contains certain numbers and trying to sort it. If that is what it is supposed to do, then while running it will need certain resources like the CPU time. The program is running on the CPU, so it will need certain time on the CPU. Sometimes the program may contain instructions, C instructions like malloc, in which case it needs additional memory. So, where the data is going to store. Sometimes it is going to create some files on the hard disk. So, these resources are what are needed by the process while it is running. To get these resources, it will make the request to the operating system, and while the program is running, certain resources are allotted by the operating system for its proper functioning. When the process is running, it may ask for additional resources depending upon the need. So, the operating system manages the process while it is created, while it is running. So, let us see the interaction between the two. In the simplest form, let us look at a processor, a very basic processor like 8088, which has got about 256 kilobytes of main memory, which has got an input device and which has got an output device. Typically, this will be a desktop kind of environment. So, when the IBM PCs, which is one of the most common architectures today, when they were designed using the existing processors that were available like 8086. These processors, they allowed only one program to be run at a time. So, the user runs a program, it terminates, the OS comes back and then the next program is loaded. So, this is a typical example of a processor that existed when the first desktops were made available, like it had a Intel CPU, certain amount of memory and the basic operating system like MS-DOS. So, when the program was running, the control to which was transferred by the operating system, the program had all the resources at its disposal, it had control over all the resources that were available. So, this diagram shows how it would work. So, here you have the operating system comes up, then the loader comes up when the user types in a name of a file. The first process starts, the process is running, in between it may be asking for the certain system calls, the system comes in which is a part of the operating system, then again comes back to the process finishes, control comes back to the OS, the user types in a new program P2, the loader then runs P2 runs, finishes execution, OS gets the control back. So, what we have seen here is the processor is able to run only one program at a time. It could be the OS, the loader, the actual user program or another user program after the first one finishes. So, this is the way in the simplest form, like an operating system like MS-DOS, which is a single tasking sort of operating system, manages running of the user programs. Now, when you want to make optimal use of CPU, a technique called as multiprogramming is used. For that, you need to schedule programs one after another on the CPU. So, that is the fundamental characteristic, that you have to do scheduling of various programs on the CPU. In the previous slide, we saw that a single processor system can run only one process at a time, whereas other processor may be in the memory, but they cannot run unless the CPU becomes free. the objective of multiprogramming is to keep the CPU as much busy as possible. In which case sometimes there are something called as terminate and stay resident programs which are running all the time. They remain in the memory and they get invoked at regular intervals. Looking at the normal programs, multiple programs which are in the memory of the CPU, one such program will be run by the OS. It will keep running till it gets into a mode where it is, let us say, reading some data from an IO device, or which is an input from the user, or it could be a file from the hard disk. It makes the request, but that request is going to take the time. If you have a DOS like operating system which does not allow another program to come in because the control has been transferred to the running program, the CPU sits idle. This is where multiprogramming comes into picture, where the idle times, such idle times are used to run another program. So, the another program is also ready to run in the memory. In such case, the operating system takes the control of the CPU from the waiting process and gives it to another process. When the another process gets into it, the first process comes in. So, what multiprogramming is trying to do? It is trying to keep the CPU always busy, thus making optimal use of the CPU. Now comes another way of achieving the same thing, which is called as multitasking. Okay. So, in such case again the CPU is single, however, the operating system has got certain mechanism where it can run multiple processes in what is called as a time sliced manner, which means when a process is started, it gets a time slice of certain milliseconds or certain microseconds. For that duration the program runs, and when the slice gets over, when the time slice gets over, the control comes automatically back to the OS. What is important to note here is that a hardware support is needed in the CPU to accomplish this. Let me point out that in an 88 based or an 8086 based system that we described in the previous slide, such a facility was not available, but processors like 286, 386, 486 and the subsequent processors from Intel, they had the support in hardware to accomplish this. So, as mentioned earlier, each process gets a slice of time to run the CPU. When the slice is over, control comes back to the OS. Another process which is in the memory, that is run. As a result, what is happening is that either when the time slice finishes or when the process is waiting for an IO operation, as we said in the previous slide for multiprocessing, or some event to take place, any wait that a running process gets into, that time is used for running another process. If there is no wait, then the time slice will get over, and when the time slice gets over, the next task will come into picture, it will start running, and as a result the CPU's optimum use will be made, and multiple tasks which are in the memory, they will keep running one after the another. So, this diagram explains how this works by taking example of two processes P1 and P2. For each process the state is indicated here, that it could be executing or in idle state. So, let us see what happens with respect to time as it moves from top to bottom. So, first process is running, which is indicated by this blue arrow. At that time an interrupt occurs or some system call is made by the P1. So, at this time the OS gets control, it will save the state of the process in what is called as process control block 1, which pertains to process 1. Now, it has to load process 2, which is currently in idle state. So, what does it do? It will load the state which was saved earlier for process control block 2 of process 2, that will start running. Now, here process 2 is running, it is in execution mode. Then again it gets into an interrupt, time slice over or a system call. It will save the state of process 2 in process control block 2 and it will reload the state of process 1 into process block 1 and process 1 will start executing. This thing that we just saw is what is called as context switch. So, context switching from process 1 to process 2 is done by the operating system with the help of the hardware that allows this to happen, which consists of timer and other things which support the operating system in doing this kind of switch from process 1 to process 2. Now, we introduce another concept which is called as a thread, having understood how multitasking is achieved. So, definition of thread is that it is a lightweight process which is a basic unit of CPU utilization. In the traditional form, every process had single thread, but today the modern processes, they consist of multiple threads. So, there are some things which are unique to a thread and there are some things which it shares with other threads of a process. So, a thread consists of a thread ID, it has got a program counter, it has got a register set and a stack which is unique to every thread, whereas what is not unique to it, what it shares with other thread is the code, the data and the OS resources like files that are open for reading and writing. The basic reason for having multiple thread is that a process which is consisting of multiple threads can perform multiple tasks. Another motivation is that a single application is required to perform similar tasks like a web server. A web server connects to multiple browsers at the same time. These multiple browsers are run by different users connected over the network. The task is same: get a request, service the request, get a request, service the request. So, each of such request is handled by an individual thread. So, this diagram shows the difference between a single thread wherein you have every thread has a code, data and files, it has also registers and stack. So, now here it tells in multi-threaded process the code, data and files are shared across the threads, whereas individual threads maintain their own registers and stack, as can be seen here that it is partitioned. So, the benefits of threads include responsiveness, that is, even if one of the thread is stuck, other threads can respond. Then it has effective sharing of resources, because some of the things are common. We saw in the previous slide that the code, data and open files are common. Then you can finish the task faster because switching threads is easier, is quicker, because the context switching is faster. Further, it is well suited for multiprocessor architecture, as we shall see in the next slide. So, the scheduling criteria for the thread switching takes care of following attributes, that is utilization of the CPU. The thread switching tries to keep the CPU as busy as possible. It also tries to maximize the throughput, that is, in a given time multiple threads are run, thus the output that you get is more than a single thread would have been able to give. Then you also have a better turnaround time, which allows a process to be completed faster. And when you look at the waiting time, you will find that the cumulative waiting time is reduced. The time that a thread spends waiting in a queue is much reduced. That is why a multi-threaded architecture is better suited than a single threaded architecture. Now, let us see how the multi-threaded architecture helps in scheduling the task on a multiple processor. This diagram here shows how a multiprocessor architecture is. You will find that the difference lies in multiple processing unit. Each has its own dedicated memory, and through a communication network they are able to communicate with each other. So, in a multiprocessor architecture, it is possible to schedule the threads on multiple processing elements rather than sharing them in a time sliced manner on a single processing element. So, there are two ways of doing it. In asymmetric multiprocessing, there is a master processor which schedules the threads on the slave threads. In the symmetric multiprocessing, what happens is every processor has an access to the pool of threads. Once a thread is over, it goes to the pool, picks up the next thread and runs it. Here it may be pertinent to introduce what Intel calls as hyperthreading. So, here it runs on a core. So, what Intel has done is the CPU exposes 2 execution context per physical core. What it means is that one physical core has 2 logical core. So, how are these logical cores implemented? So, it implements certain portions of the CPU, certain portions of the core, it duplicates it. So, it is going to take more area on the die, but because of which it allows sharing of one set of execution resources. That means there is a core which has got execution resources which are shared between the 2 threads, which are called as parts of a multi-thread, multi-hyper-threaded architecture, and as a result, if you are running a single thread, there is no loss, but when you are running a multi-threaded application, you have got a mechanism by which two threads can run on a single physical core, which are treated as 2 logical cores. So, this tries to make sure that the idle time is reduced, because when 2 threads are in a hyper-threaded mode run on a single physical core, then in that case you are going to improve the performance. Intel claims that this goes by up to 30% in certain workloads. Now, this setting of whether to allow hyperthreading or to disable hyperthreading is done through BIOS setting. That means while booting the system you have to enable it. For HPC workloads, typically hyperthreading is disabled, because as we will see later, there are in the HPC stack of a cluster, the resource manager manages the threads on a CPU, hence hyperthreading is disabled, but in normal desktops hyperthreading can improve the performance. So, before we end up, the summary is that the basic architecture that we saw in the first slide is common for all computing platforms, because essentially it consists of CPU, memory and IO. Then when you have multiple processors, Flynn's taxonomy tells us how single or multiple instructions on single multiple data streams build up 4 types of architecture. The earliest implementation of CPU like 8086 were capable of running only one program at a time, and as a result it could not make optimum use of the CPU time. To make optimum use of the CPU time, different programming models like multiprogramming, multitasking, multithreading were introduced, which were done through a combination of the operating system and the CPU resources and additional dedicated hardware like timers and context switching hardware, which were implemented by the CPU manufacturers. Hyperthreading was another step forward, where one physical CPU allowed to be viewed as a 2 logical CPUs. However, the execution unit was single, but 2 threads which were active in the memory were repeatedly switched in a hyperthreading mode to further improve the efficiency of the CPU for certain type of workloads. With this we come to the end of this lecture. Thank you.